Hello everyone, I'm Xiang Li, a PhD student from Tsinghua University. So in this talk, TuDoor attack systematically exploiting logic vulnerabilities in DNS response preprocessing with malformed packets. We find new size of DNS-based attacks named TuDoor. Before the details for the attack impact, our TuDoor attack could point the arbitrary domains within just 1 second. So in the following, I will introduce how it works. To start with, in today's internet communication ecosystem, DNS plays an important role, translating domain names to IP addresses. It also provides a solid basis among multiple applications and services. According to our VeriSign stats, more than 350 million domain names have been registered until now. So DNS is constructed in a hierarchical namespace. As shown on the right, there are different authoritative zones maintaining the DNS records from the top to the bottom, the root, TLD, and STLD. After domain registration, a new branch is created and the zone is dedicated. There are multiple resolver rules, such as forwarder and recursive, and the iterative resolution process works in a client and server style. So here is how DNS resolution works. Before resolution, a domain example.com is registered. So the DNS client begins to send a query, and the configured forwarder just transmits query to the upstream server. Then the recursive resolver does the iterative process with different authoritative servers until it gets a valid response. The response will be cached by all resolvers. As for DNS packet, two fields are used to match the query and the response, the source port and the TXID. All of them have the 6-bit space. So, since DNS is the cornerstone of the internet enabling multiple critical services and applications, attackers have long been trying to manipulate its response for hijacking their cache poisoning attacks. So what is DNS cache poisoning? Because DNS is primarily over UDP, attackers want to inject forged answers into resolver's cache. To inject forged answers, there are two ways, the on-path and the off-path. So the on-path attack could observe the network link and return response directly, while the off-path attacker needs to guess the identification fields. And DNS cache poisoning is like a cat and mouse game. After it had been disclosed, the new attacks have been continuously developed. Here I will present a famous on-path cache purif attack. Cache purif wants to inject forged responses from the on-path, so on his own authoritative server he can observe the identification fields. So cache purif queries the target resolver for his own domain alternate and return responses from his own authoritative server. So besides the forged internet.net NS records are included, then the resolver trusts the fake internet.net record and uses it for future queries, which is hijacked. So the root cause is that there lacks data verification for responses. To mitigate the cache purif attack, Badwick checking proposed only answers from the same domain as the request name are acceptable. For instance, example.com is a Badwick, where mybank.com is also Badwick and should be removed. So after the cache purif attack, Badwick checking is widely implemented, and on-path DNS cache poisoning seems impossible. So the second one is the famous on-path, off-path Kapniski attack. Kapniski tries to inject forged responses with a birthday paradox. So after the target resolver sends out the query, the attacker sends multiple forged DNS responses to it before the legal response. So each response has a different TXID. If the TXID matching, the attack succeeds. Otherwise, the attacker sends the attack again with another subdomain and does the same work. Since the TXID only has the 6 bits, the attack could work. So to mitigate the common-scale attack, source port randomization is added to increase the identification field guessing entropy. So totally, the guessing space is 32 bits and hard to brute force. So after the common-scale attack, source port randomization is integrated into the resolver's implementation, and the off-path attack seems difficult to conduct. So the third attack is the fragmentation-based attack. The attacker uses the vulnerability and tries to inject forged responses by exploiting the second fragment without checking, because there are not verification fields in fragment 2, but the attacker needs to get the TXID and the IP ID. So after the target resolver sends out the query, the attacker forces the fragmentation on the authoritative server and sends forged fragment 2 to the resolver. Then the resolver will resemble the legal fragment 1 and the rogue fragment 2. Then the forged response will be cached. So to mitigate the fragmentation-based attack, IPID randomization is added to increase the identification field guessing entropy. Besides restricting fragmentation, such as reducing the packet size for packet to TCP, and adding new validation fields also work. Then after the fragmentation-based attack, IPID randomization is widely adopted, and it is difficult to conduct. However, our lab found by increasing the packet size with a same chain, fragmentation-based attack could still work. The fourth one is a famous side-DNS attack. So by using the Linux kernel side channel, attackers could use a global counter to expose the in-use port. Then to attack the target resolver, the attacker mutes the authoritative server first, and after the target resolver sends out a query, the attacker probes the source port using the side channel and brute force the TXID. If the TXID matching, the attack will succeed. So to mitigate the side-DNS attack, SMP global rate limit counter randomization is implemented by Linux kernel. Besides reducing domain resolution timeout, and DNSSEC also work. So after 26 years, does bandwidth checking work as desired after we fixing cache purif attack? I think the answer is not, because marginal DNS breaks this guarantee with a new vulnerability for cache poisoning. So marginal DNS exploits the bandwidth checking vulnerability to inject the response into the forwarded cache shared with the recursive. So after the target resolver sends a query, the query will be forwarded to the authoritative server or another upstream server. Then the attacker sends forged DNS responses to it before the legal response. Then all future queries will be hijacked, including the TLD domains. So to mitigate the marginal DNS, developers should align the bandwidth checking logic for both forwarders and recursives, and add bandwidth checking to the forwarders. Then marginal DNS receives widely impact from the world, including government third report and over 60 medium coverage. Now, we wonder why is the new DNS cache poisoning attack still possible after researchers and vendors did a lot of work. We found that the DNS response pre-processing logic has never been studied thoroughly. So it is necessary to provide a systematic analysis of the DS response processing logic and expose potential threats. That's what we did in this paper, and we found after doing this, we found a new DS cache pausing attack, and the history not over yet. So TuDoor attack is proposed by our live, and it is a new set of powerful DS-based attack, including DS cache pausing, DOS, and resource consuming. So among them, TuDoor could poison vulnerable resolvers just within 1 second. Because we exploit vulnerabilities of DS response processing logic, like passing a convert response store in the grid wall. So we call it the TuDoor attack. So by exploiting the convert set channel vulnerability in DS response processing logic, the attacker just needs to attack once with a success rate of 100%. However, for the traditional attacker, the attacker needs to attempt many times with a low success rate. So the threat model is shown here. Our attack target includes all resolver rules. So when attacking, first we identify the target resolver, then we trigger different vulnerabilities based on the resolver rule, then lastly we conduct the attack. So to find the vulnerability, we conduct a comprehensive analysis of the DS response processing logic, and we construct processing state logic for 28 DS software, and conclude the general processing logic. And based on the basic logic, we found many implementations are vulnerable to spatial packet processing state. And we list several vulnerable state transitions here. So the red lines shows vulnerable state transitions, such as bound, unbound, keynote, resolver, and power DS. All of them have some special state transitions, and the developers didn't cover all the state transitions and miss some spatial malformed packet processing. So for example, for Microsoft DS, if it receives the new DS query packet in state 5, when waiting for the responses, it will accept this new query and start a new resolution for any domains, which leaks the source part for DS cache pausing. So basically, in state 5, Microsoft DS should only accept responses with a QR flag equals 1, not 0. So this is the vulnerability. So in summary, we found 24 DS software are vulnerable to cache pausing, DOS, and resource-consuming threats, including bound 9 and unbound, and also stub resolvers like Linux, Windows, and Mac OS. So all 4 DS programming libraries, including Python, Golang, JavaScript, and Java, are also affected. So besides, we test 42 public DS services, and one of them, 114 DS, are vulnerable to cache pausing. And the 17 resolvers such as ADGuard DS, Baidu DS, OpenDS, and Cloudflare are vulnerable to the DOS. So we, based on these vulnerabilities, we proposed 3 attacks by exploiting the TuDoor. So including the cache pausing, DOS, and resource consuming. For example, when conducting the cache pausing, the attack steps are shown right. So By exploiting one new side channel vulnerability, the attacker could expose the source port within just 1 second, with only 65 key packets. So the vulnerability here is that when the target resolver sends out a query with an ephemeral port, then the target resolver should only accept the responses on this port. However, for the vulnerable resolver, when attacker sends a query packet to these potential ports, if the packet hit a correct port, the target resolver will accept this query and send the query to the corresponding authoritative name server. So if the attacker wants to prove this port, he or she can embed the target port number to the query name, domain name, and just waiting for queries on the authoritative server. So if he or he can observe this query, they can locate the source port and then just brute force the TXID to inject the fake responses. So after 20 experiments, the average attack time is only less than 0.5 seconds, which is 201 keys times faster than prior attacks. So with design probing policies using XMAP, we found that there are 423 key resolvers are vulnerable to TuDoor attack. And among them, there are about 200 resolvers are vulnerable to the DS catch poisoning attack. So as vulnerability disclosure, we reported to all affected vendors, and TuDoor is confirmed by all affected software. In the end, 33 CV numbers are assigned, and we got a bounty awarded by Microsoft. Then, for the root cause, we found that not all the response pre-processing data are considered by the software. So we're suggesting standardizing the DS response pre-processing logic to consider corner processing cases. Specifically, resolvers should avoid a time window for promising normal response and ignores queries sent to non-fixed reports. We also released online tools to detect vulnerable resolvers. So this is my share today. Thank you all for your attention.